Welcome to this new video about set theory. Today I will finally introduce the axiom of the Zermelo-Fraenkel Axiom system. I will not introduce all the axioms at this stage, because some axioms might appear to be ill-motivated. I will introduce them in a later video. I will also introduce some basic constructions of set theory, for example intersections. And finally, I will also introduce the notion of class.
In our previous video, I have introduced the notion of a well-formed formula. I have also stated that we must be able to write any formula as a well-formed formula. In particular, in order for the axioms to be valid, we must be able to write them in the form of a well-formed formula. First, we will recall a convention. The convention is that everything we will discuss is a set. So for example, if we write for all x, or there exists an x, then this x is a set. Let's begin by recalling the logical axioms about equality. These axioms were the following. The first axiom states that for all x, x equals itself. The second axiom says that if phi x is an arbitrary well-formed formula, then the following axiom holds: for all x and for all y, if x equals y, then phi x if and only if phi y. So any formula about x must also hold for y, if x equals y. Now we can finally introduce the Zermelo-Fraenkel axioms. The first axiom is the axiom of existence. This axiom states that there is at least one set. So the axiom system is not void. The axiom, however, does not give any details about the set that exists. It could be empty, it could be finite, it could be infinite. Now, in order for this to be a valid axiom, we need to be able to write this as a well-formed formula. Now, it is tempting to write the following: there exists an x. But this is not a well-formed formula. You cannot only write a quantifier. So we add the following: there exists an x so that x equals x. The next axiom is the axiom of separation. In the naive set theory of Cantor, any formula phi x defines a set, namely the set of all x so that phi x holds. As we have seen, this gives rise to Russell's paradox, so we cannot accept this as a valid set. In fact, what will be a valid set, that if we are given a set A and a formula phi x, then the following will in fact be a set in our axiom system: the set of all x elements of A such that phi x holds. In other words, given our set A, we can separate the set into two sets: the set where all phi x holds and a set so that the negation holds. And this set is exactly this. Hence the name axiom of separation. In this way, Russell's paradox does not show up. Indeed, we have defined the Russell set as the following: x shows that x is not an element of x. But as we have seen, this is not a valid set. In order to obtain a valid set, we need x to be an element of some set already. So the following would be a valid set: set of all x elements of A such that x is not in x. Now let's try to replicate Russell's paradox. So again, we demand if R is an element of itself. So in the first case, if R is an element of R, then two things must be satisfied. R must be in A, and R must not be an element of itself. This again gives a contradiction. But the other side, if R is not an element of R, then there are two possibilities. Either R is not an element of A, or R is an element of itself. But this does not give a contradiction, because we cannot conclude that R is an element of R, because we can also conclude that R is an element of A, and because this possibility arises, Russell's paradox does not in fact show up. Let us now try to write the axiom of separation as a well-formed formula. The well-formed formula is as follows. For all sets A, there exists a set B, so that for all x holds that x is an element of B, if and only if phi x holds and x is an element of A. This is a well-formed formula. Again, it is not one axiom, it is actually an axiom scheme. Indeed, for every formula phi, we have a different axiom. In particular, we can now show that the empty set exists. Indeed, from the axiom of existence, we have that there is at least one set A. So axiom of existence gives the existence of a set A. Then by the axiom of separation, we can form the following sets, namely the sets of all x elements of A, such that x is not equal to x. This is of course shorthand for not x equals x. This is indeed an empty set. Indeed, suppose that this set has an element. So suppose that some x is an element of this set, then it must satisfy that x is not equal to x. But this can never be satisfied. So this is a contradiction. So there cannot be an element of this set. So it is indeed an empty set. Now, is this empty set unique? Is there a unique empty set? To answer this question, we need a new axiom. This new axiom is the axiom of extensionality. This axiom tells us exactly when two sets are equal. The axiom says that two sets are equal if and only if they have the same elements. If we write as a well-formed formula, then we have the following. For all x and for all y, if for all u holds that u is an element of x, if and only if u is an element of y, then follows x equals y. So any element of x is also an element of y, and if every element of y is also an element of x, then the two sets must equal. Now we can also write the converse of this, so we can write an arrow here, and this says that if two sets are equal, then they have the same number of elements. But we do not in fact need to write this, because it is a logical axiom. The logical axiom about equality says that if two sets are equal, then they satisfy the same formulas. Now, let us prove that there is only one empty set. So let's assume that x and y are both empty sets. We need to prove that any element of x is also an element of y. So if we take an element of x, but there is no element of x, so any element of x is also an element of y, vacuously, because there are no elements of x. And conversely, since y has no elements, any element of y is also in x. So from the axiom of extensionality, it follows that there is a unique empty set. The axiom of separation gave us the existence of the following sets. Set of all x in y, so that phi x holds. This is the axiom of separation and provides us with this set. Again, the axiom of extensionality proves that this set is in fact unique. Let us now introduce some basic constructions. For example, let us introduce intersections. So, given any two sets A and B, we should have that U is an element of the intersection if and only if U is an element of A and U is an element of This should be the definition of our intersection. So we can define the intersection as follows. A intersect B is the set of all U such that U is an element of A and U is an element of B. But of course, this is not a valid set. The axiom of separation does not give that this is a valid set. We need this to be a subset already of something else. But recall, the intersection will always be a subset of A. So we can as well write this as the set of all U in A, such that U is an element of A and U is an element of B. This is a valid set according to the axiom of separation. We can as well write it, of course, as U element of A, such that U is an element of B. This defines the intersection of two sets. More generally, if A is a set, then we can form the intersection of all of its elements. So we can form the following sets. Intersect A is a set of all U, such that for all Z in A holds that U is an element of Z. So intersect A is the set of all the elements so that U are in all elements of A. Now recall, this notation is just a shorthand. So for all Z in A, phi Z is just a shorthand for all Z. If Z is an element of A, then phi Z. And likewise, there exists a Z in A, phi Z is a shorthand for there exists a Z, so that Z is in A and phi Z. Of course, in order for the intersection to be a valid set, we need to modify its definition a bit so that it satisfies the axiom of separation. So assume first that A is not empty. Then there exists some Z naught in A, and then we can define the intersection as all U in Z naught, so that for all Z in A, U is an element of Z, and this is a valid set. Now, if A is empty, then the intersection will be left undefined. We can also form the set difference. So, difference between two sets is defined as the following. All elements of A, so that U is not an element of B. Another consequence of the separation axiom is that there is no set which contains all the sets. So if V, for example, is a set which contains all the sets, then we can form, for example, the following set: all X in V, so that X is not an element of X. This is of course just the Russell set. But if V is a set, then by the separation axiom, R must also be a valid set. And then, just analogous with the Russell paradox, we can show that R is not a set, we can show that it yields a paradox. So we must conclude that V is not a valid set. Now, so far, we only have the empty sets, and we have no other sets. So now we will see some axioms that provide actual new sets. The first axiom, which will actually provide new sets, is the axiom of pairs, and says that if A and B are two sets, then we can form the pair A and B, and this is a set which contains exactly A and B as elements. If we write it as a well-formed formula, then we get the following. For all A and for all B, there exists some set C which contains A and it contains B. Now, notice this is not exactly what we want. C is just some set which contains both A and B. But we need a set which contains exactly A and B. But this is easily solved by the separation axiom. So we define the pair AB as a set of all x in C, so that x equals A or x equals B. So AB is now the set which contains exactly A and B. Extensionality now provides that this set is unique. Furthermore, extensionality implies that the following sets are equal, so the order does not matter. Indeed, both sets have exactly the same elements. Furthermore, we make the following definition. The singleton A is just defined as the pair AA. Now we already know the empty set exists. So by pairing, we can now form the set which contains the empty sets. And if we apply pairing again, then we obtain the following sets. Or we obtain the following sets. And by applying pairing once again, we can obtain, for example, the following sets. So the axiom of pair gives many sets, and you can check easily by using extensionality that these sets are all distinct. But so far we can only form sets which have two elements. Indeed, all the sets we have formed here, for example, this set contains one element, two elements. So all sets we can form now either have 0 elements, 1 element, or 2 elements. We cannot yet form sets which contains more than 2 elements. To form sets with more than 2 elements, we will need a new axiom. The axiom of union says that if A is some set, then the union of all elements of A is also a set. So we can form union A is the set of all x, so that there exists a z in A, so that x is an element of z. Now the axiom of separation cannot be used here because x is not an element of some set that we already know to be a set. And we cannot find such a set. So the axiom of union is needed as an axiom to say that this is an actual new set. Now, if we write it as a well-formed formula, then we get the following. For all A, there exists a set Y, which will be the union, so that for all x, there exists a Z, so that Z is an element of A and X is an element of Z, then X is in Y. So, if there exists a Z in A, so that X is an element of Z, then X is an element of Y. So Y contains the union of all elements of A, but it is not equal to the union of all elements of A. To make it equal to the union, to actually make the union which contains exactly the elements we want, then we need the separation axiom. So we define the union as all elements in Y such that there exists a Z in A so that X is an element of Z. So we have exactly the same definition as before. The only difference is that the axiom of union now provides some sets Y that can be used as some supersets of the union. So a set which contains the union. Now given any two sets, X and Y, the axiom of pairing says that we can form the pair XY, and the axiom of union says that we can take the union of this set. So we get the union XY. We use the usual notation X union Y. And we can then also form X union Y union Z as X union Y union Z, and you can check that this is exactly the same as X union Y union Z. So this is the same, as you can easily check. Now we can also form 3-element sets. So for example, the 3-element set A, B, C is just defined as the pair AB union the singleton C. Now the pair AB exists by the axiom of pair, the singleton exists by the axiom of pair again, and the union exists because of the axiom of union. So 3-element set exists. And then we can also, of course, prove the existence of 4-element sets or 5-element sets. And now we can also check the usual set theoretic formulas. For example, we have the following set theoretic formula: A union B intersect C equals A union B intersect A union C. This is a formula that holds, and you can easily check it using the axiom of extensionality, and you can check it like you already know how to check it. So the usual set theory that we have can now be derived. Finally, I introduce the axiom of power set. The axiom of power set says that for any set S, we can form the power set of S, which is the set which contains exactly the subset of S. To write the axiom of power set as a well-formed formula, I introduce first the following shorthand. I say that U is a subset of B, if and only if for all X in A holds that X is an element of B. So this is a shorthand. Now we can state the power set axiom and state that for all sets S, there exists some set P such that for all U holds that if U is a subset of S, then U is an element of P. So P contains the subset of S, but it can contain more. So we need the axiom of separation to actually define the power set, and we can do this by defining the power set as all elements U of P such that U is a subset of S. So this defines the power set. For example, we can now form the power sets of the empty set, and we can prove that this is exactly the singleton empty set. Or we can form the power set of the singleton empty set, and we can prove that this is exactly the set which contains the empty set and a singleton empty set. And so far, all the axioms only provide finite sets. That is, we cannot prove nor disprove from the previous axioms that there exists an actual infinite set. So to actually get infinite sets, we need a new axiom. But we will introduce this axiom later. Finally, I would like to introduce the notion of a class. I've already remarked that something like X shows that phi X holds is not an actual set. The axiom of separation does not apply. The axiom of separation only applies to things like this. X element of A shows that phi X. So this is a valid set if A is a set. This cannot be proven to be a valid set. Nevertheless, it is not a bad idea to actually talk about these entities. And we will call these entities classes. Remark, however, that in the formal language, everything we work with is a set. So classes, which we will introduce now, are not actual part of the formal language. We only introduce classes for practical reasons. They are merely a very useful intuition and a very convenient way to describe results. However, formally, everything we do with classes can and should be written down as usual well-formed formulas which involve sets. However, we will use classes because classes make results more readable. This is exactly why we introduce them. So what is a class? Given any formula phi x, the following will be a class. Now this is just notation. We define two classes to be a subset of each other. So a class x such that psi x holds will be defined to be a subset of all x so that phi x holds if the following is true: if for all x, if psi x holds, then phi x holds. So this notation of a subset is exactly meaning this notation. So this notation of a subset is not actually a subset, it is just a different notation of this well-formed formula. We can also define two classes to be equal to each other if they are a subset of each other. Now, given any set A, we define A to be an element of the following class exactly if phi A holds. So this notation of the element means nothing more than this, that phi A holds. We know that only sets can be elements of classes. We cannot have that a class is an element of another class in general. This is to avoid Russell's paradox. Now, given classes C and D, we can form the following classes. C intersect D is the class of all x so that x is an element of C and x is an element of D. We can form C union D of all x so that x is an element of C or x is an element of D. We can also form the intersection, the difference of all x so that x is an element of C and x is not an element of D. And we can form the union of all elements in the class C as all x so that there exists an S in C. This S is a set, of course, so that x is an S. These are all classes. Finally, any set S can be considered a class. So given a set S, we can form the following class. S prime is the class of all x so that x is an element of S. So this is again a valid class. Now, note that x is an element of S prime exactly when this formula is satisfied. X is an element of S. So in some sense, the class S prime and the set S have the same elements. This means that we will not distinguish the class S prime and the set S. So we will say actually that S prime is an actual set. Now a class that does not come from a set are called proper classes. Some examples of proper classes are V, the set of all x so that x equals x. This is the class of all sets, or the universe. We also have the Russell class of all sets x so that x is not an element of x. This is again a proper class, it is not a set. This avoids again Russell's paradox, because a class R cannot be an element of R. We do not know how to define this. We only know how to define this if R is an actual set, but R is not a set. Pure formally, there is actually no distinction between a class and a formula. So any operations that we write as classes, we can also write perfectly as formulas. The reason to actually introduce classes is that it is easier to manipulate classes than to manipulate formulas. As far as a formal language of Zermelo-Fraenkel is concerned, there are only sets, there are no classes. Classes are only for our convenience because it is easily readable. Other axiom systems, like von Neumann-Bernays Gödel, so NBG, do actually introduce classes as a formal object. So in NBG, we have two types of objects, namely classes and sets. In the Zermelo-Fraenkel axiom system, we only have one type of object, sets, and classes are just a way to write things down. This concludes this video for today. I hope you enjoyed it.